Out every sportcaster's favorite term, and that's momentum. Coaches, everyone's like, we have to have the momentum. We lost momentum. We gained momentum. What the heck is momentum? Well, momentum is what we're talking about today. And momentum is basically like an object's desire to maintain its current state of motion. It's almost a numerical way to describe inertia. All right. So there's two things we're going to talk about, and that is momentum. And momentum is defined as it's literally divided by its own equation, as the product of an object's mass times the object's velocity. So if you are very massive and you're moving, you have momentum. If you are moving very quickly, you have more momentum than if you're moving slowly. All right. Me walking is more momentum than you walking because I'm more massive than you. Okay, so that's basic momentum. And if you look at the units, you've got mass is kilograms and velocity is meters per second. So you are looking at the ugliest units in the world of physics. Apparently, if it was a kilogram meter per second squared, we would have given a new name, like one extra letter in there, and we'd be like, oh, it's too much to write. But these are the units for momentum. And like I said, they basically just describe an object's motion and its desire to stay in motion, because if you have more mass, you're going to maintain that motion. If you're moving faster, you're going to maintain that motion. So that's basically what it is. Now, there's a flip side of this coin, and that is what's called an impulse. All right. Now, an impulse is very important because it's akin to work and energy. Okay? Energy is what you have, and it's what you can use. Work was how you changed that. How did you transfer it? Well, that's the exact same thing here. Momentum is something an object has. Impulse is how you change an object's momentum. So how you change momentum. So change momentum would be there's a change momentum. In case you have forgotten momentum symbol here, P equals mv, or rho, depends on what you want to go by. And if you are going to change its momentum, well, the way you do that is you have to apply a force for a period of time. All right, so if you want to change something's momentum, you have to apply a force for a period of time. I call this the checkout line syndrome. All right, if you've ever been in those long lines, especially around the holidays, and they want you to buy a little extra stuff. All right, or maybe you're just shopping and you got some groceries and you're in the checkout aisle. Well, you have a certain amount of momentum. You want to do something like, I'm going to buy this and I'm going to go home. Well, if they stick you in line for a long enough time, and they can apply a great enough force, maybe they can change that momentum. All right, and AK get you to buy the newest newsstand of how to lose 30 pounds and blah, blah, blah. Or whatever act's going on Cosmo these days, which is the same thing that's going on Cosmo for the last 10 years or more. All right, so this is how you change momentum, is by applying an impulse. And then momentum is what an object has. And therefore, it technically has the exact same units because the units are equal to kilogram meters per second. But if it's force times time, well, that's a Newton second. And if you remember, a Newton is a kilogram meter per second squared times seconds. Well, that makes that go with that, and oh look, we've got the exact same units. All right. Now, I don't want you to be like, oh great, something new. No, it's a lot like energy, where there's really nothing new here. It's just a new way of looking at things. So I'm going to do a derivative here. All right. So we all know this. All right. F equals ma. All right, we know that. Well, if I just simply rearrange this, F equals and really, I'm just going to be super OCD about this. F equals m, and then acceleration is defined as your change in velocity over time. Well, if I just rearrange this, F delta t equals m delta v. So what this says is if I apply a net force to an object for a period of time, I'm going to take that object and I'm going to change its velocity. Well, this right here, if I change this, that's equal to changing in momentum. And as we know, change in momentum is what we call applying an impulse. All right. So, whoops, that's not the letter I wanted to write. I just wanted to write let's see. Is a J, or often it's just wrote down impulse by itself. All right. So all of this is the equation that works out, and this is what is the big governing equation with all the equal signs, because you can say, okay, I know the impulse applied, so I know the force applied for a period of time, and again, this is a net force, and I can say, well, then I can calculate its change in velocity or its change in momentum. So all these things can be interlaced with each other, so you can go from one to the other. All right. Now the last thing I'm going to talk about is the idea that momentum is always, notice the caps there, conserved. All right, so the total momentum you have before something is exactly equal to the total momentum you have after something happens. Okay, momentum is always conserved no matter what, and this is based on the definition of Newton's third law, because when you have this net force here, okay, when you have two objects interact, they both apply an equal force to each other. All right, so if I apply a force to you, then you'll have a positive force for a period of time. Well, you then will apply the exact same force to me, but it's going to be in the opposite direction, so we'll have a negative force for a period of time. So if you look and you add these two together, you get a total change in momentum equal to 0. All right? So if you look at everything as an entire system, okay? So for the system where you could have multiple objects involved, then, I bump into you, you bump into me, we apply the exact same forces, opposite directions for the same period of time. So you'd have a positive change momentum, I'd have a negative. The total momentum of, both of our systems is 0. So that's why momentum is always conserved. But if I want to look at the single momentum of a single object, well, then that can be changed, because if I push you, well, now your momentum's changed. All right, but the momentum of all objects involved in that interaction, that total momentum will be 0 because of Newton's third law. So really, impulse momentum is defined by Newton's second law. I want a new color here, whatever. All right, so the second law is what defines what we refer to the impulse momentum theorem. All right, and then Newton's third law is what we call the law of conservation of momentum. All right. So this is kind of our introductory to momentum, and these are all the key things. And again, it looks new and it's fancy new symbols, but it's based on everything that we know about Newton's second law and everything we know about Newton's third law. All right, so next time we'll actually talk about how do we apply this, and maybe we'll start doing some math. Yay, math! Until next time, stay awesome.